Hello, everybody. Welcome to my habilitation defense. First, I would like to thank jury members for having accepted my invitation to report and to examine my habilitation. So in this talk, I'll present my work on large-scale trustworthy distributed collaborative systems. First, some words about my education and work experience. So I did my studies in Romania, and afterwards I did a PhD at ETH Zurich in Switzerland. And starting from 2006, I am in France at INRIA. And then in 2007, I was recruited as a researcher at INRIA. The work, I would like to highlight that the work that I will present is a result of collaborative work that I did mainly together with my PhD students, but also with other collaborators. I supervised 6 PhD students, and among which 4 already defended. Distributed collaborative systems allow users to collaborate on a set of shared documents from different places at any time and from different devices. Examples of collaborative systems are wiki systems, version control systems, or Google Drive. If when these collaborative systems appeared, they were mainly used with only several users, for instance, for writing a research paper. And cases when people would want to edit the same line were almost inexistent. But nowadays we notice a change in the scale from several users to a community of users. For instance, open source projects where we have a community of developers that contribute to a code of a common software project, or Wikipedia, where during an important event, many users modify the wiki page related to that event, or during a conference where we have a community of participants that take notes during a presentation. I'll give an example of large-scale collaboration from Wikipedia. Wikipedia is the largest knowledge repository in the history of humanity that has been written collaboratively by a lot of users. We have about 42 million users that contribute to Wikipedia, and Wikipedia contains about 56 million articles. But despite its size and the large number of users that edit it, the mechanism for integrating user changes is quite primitive. So merging at parallel modifications on the same page is not automatically performed. If you have 2 users that are concurrently editing the same article, when they try to save the changes, the save of only one user succeeds, but the other one will fail. The changes of the user whose save succeeds are published, and the other user will have to resubmit his changes. If this works well for a few users, there are several issues in the case of community of users. Here is an example of a revision history of a Wikipedia page of United States Capitol that was extensively modified during the attack of Capitol on January 6th this year. We can see that there are a lot of changes that have been done in very close time, and we see, for instance, here we have 3 changes that were done in the same minute, or later on at another 3 changes that were done in the same minute. So a real-time collaborative editing of wiki pages would be more suitable in these cases. Most commonly used collaborative systems are those provided by large service providers such as Facebook or Google. While these collaborative systems offer very interesting functionalities, they also feature certain limitations. They rely on a central authority which stores user personal data and has the control over user data, which is in fact a perceived threat of privacy for the users. These systems do not scale well. we can see in terms of the number of users and the frequency of their modifications. We have done some simulations, and we have seen that, for instance, in Google Docs, starting from 30 or 35 users that edit on the same time on the document, the system becomes unusable. Additionally, for existing systems with a central authority, administration costs are very high, and only a large service provider can afford paying these costs that are not shared. Our vision is to build decentralized collaborative systems, in fact, that eliminate the disadvantages of centralized systems. Each user in this peer-to-peer collaboration, each user maintains his data and decides with whom to share it. We suppose that each user has a replica, so we denote in this way that each user has a replica, and modifications done by user we will denote with a star. Here we have that one user sends his modification to some other users, which at their time, at their turn, they will send the modifications through the other user, and in this way, the modification will reach everybody. For instance, we can deploy this collaborative collaboration, peer-to-peer collaboration, by using web technology such as WebRTC. And also in these peer-to-peer collaborative systems, the risk of privacy breaches is decreased, as only part of the protected data is exposed at any time. As other strengths of peer-to-peer collaborative systems are high scalability, resilience to faults, and that they allow sharing administration costs. In this collaboration, we still have servers, but they behave like users. For instance, for correcting misspellings or for an automatic translation. We can consider in this way that we have a man-machine collaboration. So in this collaboration, we would like to support concurrent changes when we have that users write changes at the same time in a shared document. And here we have, for instance, this user is doing a modification. The other one is also doing a modification. And then when they will share this modification, so when one user is receiving the modification, some conflicts might happen. And these conflicts are more difficult to resolve when they refer to the same part of the document. We also want to support offline work when a person is disconnected from the network. So we have here that this user is disconnected from the network, and she can continue to work in isolation. All the other users do some modifications locally. Okay, and then the users that are online, these people here, they will be able to exchange the data. So, for instance, this user will receive the data, and we see that this user, while he's offline, she doesn't receive the modifications. But then when she will have again network, so when she's becoming online, she will send the modifications to the other user, and then there we might get some conflicts. The example that we have seen previously was an example with a network partition with a single user that was offline, but we want to support also offline work when you are disconnected from the network, and these network partitions can exist due to network non-availability, or also due to the fact that some groups want to work in isolation and be able to share the data only among themselves before submitting them to the whole group. So, for instance, here we have these users that work in some groups, An example can be in a project where we have several institutions. We can imagine that one institution would like to validate the work among the members of that institution before sending the updates to the whole group and to the all partners. In this ad hoc collaboration, is also possible to have some overlaps among groups. We also want to support group awareness, that is, what information to provide to users to understand changes of other users and prevent conflictual changes. For instance, if users work in subgroups on shared documents, so here we have these users that work in a subgroup, okay, and then we have the other user, the other two users that work in a subgroup. They also can exchange their modifications among themselves, but not with the other subgroup. We want to, so when these two users work together, we want that they are still available, they are still aware of some changes of the other group, maybe not the complete changes, but at least some sort of information about the localization of changes, which will help them prevent the conflictual changes. And for instance, in this case, we can imagine that this subgroup of users will send some information, some ghost information, for instance, about the localization of their changes. In this peer-to-peer environment, we need a peer-to-peer security mechanism without a central authority that is scalable and easy to use. Traditional security mechanisms do not satisfy this criteria. They are not suitable as for performance reasons. We cannot send a request towards a central authority and wait for checking access rights each time a user types a character in the document. Also, in the context of a federation of organizations, it is also difficult to agree on a central authority who would maintain all access rights. In my work, I investigated how to replace traditional hard security mechanisms with soft security ones. So here, rather than adopting an a priori strict enforcement of security rules, access is given first to data without control, but with an a posteriori verified restrictions. In the peer-to-peer collaboration that we envision, users share the data with some people they trust, and these trust values can be dynamic and vary during the collaboration. For instance, I could trust a person at the beginning of the collaboration, but I can be deceived during the collaboration, and I would not trust her anymore, so I would not want to collaborate with her anymore. So in this peer-to-peer collaboration, data is replicated, and one of the main challenges that I addressed was how to maintain consistency of these replicas in the face of concurrent modifications. My research axes can be divided in two. So one of them is collaborative data management, and the other one trustworthy collaboration. So about replication algorithms, I want to develop replicated algorithms that are reliable, scalable, and explainable. Reliable because after the reception of all changes, copies have to converge. The algorithms have to be scalable and have a complexity that does not depend on the number of users. And these algorithms have also to be explainable and also understandable by humans, and the user intentions have to be respected. I evaluate these algorithms by means of their theoretical complexity, but also using collaboration traces, and also by means of user studies. I also developed group awareness mechanisms. In the second research axis on trustworthy collaboration, I addressed the question on how to evaluate collaborators' trust in order to share them the data. And in the next, I'll discuss about each research axis. So about the first one on collaborative data management. In the research field of replication algorithms, we have two families of algorithms, operational transformation and CRDT. Operational transformation is a family of algorithms that was proposed around 90s, and several optimizations followed. It is the mechanism that was adopted by Google since 2010. Here's a very simple example to understand how it works. The document is seen as a sequence of characters, and the operations specify the position of insertion or deletion. So here we have a document, concurrency control, that we see it contains two misspellings. Here it's missing an R and here an O. And we suppose that one user wants to correct this misspelling here, so it's inserting an R at position 7, while the second user inserts an O at this position, which is position 17. So when this user transmits the operation to the first one, the operation cannot be applied as it is on position 17. Its position has to be adapted because an insertion happened before. So now the position 17 of insertion becomes 18. The advantage of operational transformation is its genericity. While we have a single algorithm that can be applied for all data types, and afterwards transformation functions have to be proposed for each data type. The disadvantage is the time complexity. In the best case, we have O of h squared, where h is the list of all executed operations at a site. Also, with operational transformation, it is difficult to write correct transformation functions, and usually either they use a server for doing the synchronization, or they use state vectors for detecting concurrency, which poses some problems of scalability. While operational transformation it is suitable for small groups of users that want to collaborate, it is not very suitable for large-scale peer-to-peer collaboration. Since about 10 years, we work on another mechanism called the CRDT, conflict-free replicated data types, as opposed to operational transformation, which transforms operations in order to make them commute. In CRDT, we have to define data structures where concurrent operations commute by design. In our example, each character is associated with a unique identifier, and a total order exists among these identifiers. And these identifiers, in fact, they determine the order of the document characters. So it is always possible to insert an identifier among two other ones, and we call this a dense total order for the identifiers. There are different approaches for generating identifiers, and an example is Logut team, a Logut that was algorithm that was designed by our team. The Logut identifier is composed of it's composed of a triple. We have a position that determines the order of the identifiers, a site identifier, and a logical clock. If we wish to insert a character between two others, so as we have in this case, so what we need to do is to generate an identifier that is between this one and this one, and we would generate this kind of identifier. The same here, when we have an O here, we would generate an identifier that is in between this one and this one. So the advantage of CRDT is that they have better performances in terms of time complexity, and we do not need concurrency detection. The main disadvantages is that we have to design a a specific CRDT for each data type. And also another problem is that identifiers have a storage cost, and we will have a metadata overhead. But these approaches are suitable for large-scale collaboration. My contributions relate to three main problems: algorithm design, their evaluation, and conflict prevention and resolution. About algorithms design, so I contributed to both families of algorithms, OT and CRDT. We developed an OT algorithm for complex data, such as hierarchical text documents, XML, and wikis. In order to deal with the metadata overhead, we proposed a CRDT approach for strings, and we also proposed undo mechanisms based on CRDT. For the evaluation of algorithms, we evaluated them according to theoretical complexities, and we did an evaluation of OT and CRDT algorithms, but also using traces of collaboration. We also measured the delays in real-time collaborative editing systems, and also the influence of these delays on users. Concerning awareness mechanisms, we proposed some awareness mechanisms for source code and textual document that also consider user privacy. And we also analyzed traces of collaboration generated by Git projects and real-time collaborative editing, such as Overleaf. So I will not be able to explain all my contributions, and I will focus here on two of them because I chose them because they show different aspects of my research work, from algorithms to building a collaborative system, testing its performance from system point of view, but also from a user point of view. So we have seen that disadvantages of CRDTs are metadata overhead. So in order to address storage cost of identifiers, we developed a loggood split algorithm, a CRDT for sequence. Compared to loggood, so rather than identifying each character, here we identified a string, so a sequence of characters. Each identifier is composed of two parts. We have a base and an interval. The base is composed of a sequence of identifiers here, a sequence of integers, sorry, a site identifier, and the logical clock. And the interval, it's containing the beginning and end of the interval of the string. The main principle of loggood split is the fact that when an insertion occurs in the middle of a block, we would split the block. In this example that we have previously, we have concurrency control, and we would want to insert an R at this position, an R, so between concur and NC control. So what we do, we would generate the two blocks. We split this block in two, so concur and NC control. And here we have the identifiers of this block and of this block. They contain the same base as the original block we see here. And then the interval was split at the position of insertion. So here we have the identifier from 0 to 5. And for the second block, we have the interval from 6 to 16. And then we have to insert an R in between. So this will be another block. And now we would have to generate an identifier that is in between the two blocks. And then the mechanisms that we apply is that we consider the base, okay, and then we consider the end of the interval of this block, so which is 5. Then we add the site identifier, its clock, and then here we have the interval concerning to related to the string that we insert. The same thing when we would insert an O here. So we would need again to split this block into two, and we similarly do. So we split the block into two, and we generate another block for O, the string that we inserted, which would have a new identifier. We built an editor based on this log-loop split algorithm that is called mute. By means of simulations, we measured delays experienced by users in mute, which write characters with a certain frequency. Delays can be defined as the time that a modification done by a user is visible to the other users. We see here, so for a typing frequency of 2 characters per second for each user, we have seen delays that are less than 2 seconds. Okay, and we did the same measure for Google Doc. Be careful, here we have a change in the scale. So before we had here delays that are less than 2 seconds. Here we have delays that are even about 20 seconds. So by seeing these delays, we can question its impact on the collaboration. Delays can be due to to several reasons. We have network delays, we have the complexity of synchronization algorithms, and the type of architecture where the computation can be done on the server or completely on the client side. For studying this question on the impact of delay on users, we did a user study for understanding how delay affects performances of a group. In collaboration with the Department of Psychology from Wright State University, in the context of INRIA US Cost Associated team, we organized an experimental design with users. We recruited 20 groups of 4 users, and we asked them to perform several editing tasks using an editor. And then what we did is that we inserted delays of 0, 4, 6, 8, and 10 seconds without that users are aware of these delays. I report here the results that we obtained for the note-taking task. In the note-taking task, what we did is that we let users listen to an audio interview. It was about cloud computing, and we asked them to take notes on that. So what we noticed that happened is that due to delay, notes about the same topic were taken 2, 3, and even 4 times. What happened is that when 2 users want to take notes on the same topic, in the presence of delay, changes of one user are not immediately visible to the other user. So then this user thinks that the other one is not taking the notes. So he or she will also take the notes. In that way, we have finally that the notes are in double. If, as we had four users in the group, finally we would have 3 or 4 times the same notes that were taken simultaneously. And here in this figure, we have that, for instance, the idea about the dematerialization was taken 3 times. Here are the results that we obtained by analyzing this note-taking task. We have seen that the delay is increasing with the error rate. That is the number of errors that users did, and the redundancy, which is the fact that the same information was appearing several times, as we have seen in the previous example. For studying the quality of the notes taken by groups, we studied the number of keywords that have been taken by users with respect to the keywords in the audio transcription. We found out that as the delay increases, okay, we see that the proportion of the keywords decreases. So it means that the quality of the notes taken by users also decreased. The study we performed shows that the delay influences the efficiency of the group and the quality of the note taking. This finding is important because the choice of the underlying architecture of the collaborative editor, as well as of the synchronization algorithms, has an impact on the delay. If these delays cannot be avoided, then what we need to do is to offer users some awareness mechanism that can help them compensate for the delay by some coordination strategies. So this result is important. It means that we should continue our work on obtaining efficient synchronization algorithms. So as a summary of my first axis of research on collaborative data management, I can say that my contributions range from OT and CRDT algorithms design to their evaluation by means of theoretical complexity, simulations, or real collaboration traces, and also the study of their impacts on users. Regarding to awareness, my contributions range from studying the conflicts in real collaboration traces to the design and prototype of awareness mechanisms. I will start now to discuss my second axis of research on trustworthy collaboration. In the large scale peer-to-peer collaboration that we envision, an important question is how to evaluate collaborators' trust in order to share them the data. A rational decision would be based on the evaluation of their previous collaboration. But the fact that in a large scale collaboration, we cannot remember the interactions of all users with whom we collaborated, and sometimes we have a false impression on the contributions of our collaborators. We can suggest that a trust value is computed automatically according to past user behavior. A main challenge in this task is therefore how to compute this trust according to past user behavior and be able to predict future user behavior. In the context of the PhD thesis of He and Trong, co-supervised with Pascal Molly, we proposed a contract-based collaboration model where trust in users is established and adjusted based on their compliance to the contracts specified by the data owners when they share the data. Observation of adherence of or compliance to observation to the respect or violation of contracts is done by using a log auditing mechanism. Our contract-based collaboration model allows a specification of contracts, merging of contracts and modifications on the document, and also resolution of conflicting contracts. The model detects if the collaboration logs were tampered by relying on hash chain-based authenticators. In order to compute the trust score of users according to their contributions during a collaborative editing task, we need to evaluate the quality of the content of a document that has been written collaboratively. In the context of the PhD thesis of Quang-Vinh Dang, I co-supervised with François Charrois, we investigated how to automatically assess the quality of Wikipedia articles in order to provide guidance for both authors and readers of Wikipedia. In this context, we proposed 3 quality assessment methods for Wikipedia articles. The first one The first one is using supervised learning, where what we proposed, we added some readability scores in order to improve the quality of the assessment. And then we also proposed two approaches based on deep learning mechanism that automatically learns features from document contents rather than manually defining them. I also did some work on predicting trust relations between users that did not interact in the past. The problem here is that given a network in which the links represent the trust and distrust relations between users, we propose an algorithm to predict future user trust and distrust relations. We also proposed an experimental design for testing trust-based collaboration model. I'll describe in more detail this last contribution. This work on the validation on the result the validation of trust-based collaboration is in fact the result of several years of work in collaboration with the Department of Wright State University and uses a game theory. We employed the trust game, that is a money exchange game that has been widely used in behavioral economics for studying trust and collaboration between humans. In this game, exchange of money is entirely attributable to the existence of trust between the users. In this game, we have senders or investors that will send a sum of money to the receivers or brokers that would be able to invest the received money, and then the receiver can send back to the sender a sum of the money. So here we have an example here. We have this user that has at the beginning 10 euros. The second one also has 10 euros. So we have that in the first step, user 1 sends 8 euros to the second user. The sum received by the second user is tripled. So this user will receive 24. So at the end, the new balance will be 34. And then we see the balance of the first user because he sent 8 euros. The new balance is 2 euros. In the next phase, so this second user, the receiver will be able to send to the first user a sum of money that is between 0 and 24, which is the maximum sum that he received from the first user. So we see here that she sends back 17 euros, and then her final balance would be 34 minus 17 gives again 17 euros. And then the first user, he receives now 17 euros, and he has 2, so he has finally 19 euros. This trust game can be multiple shots involving multiple exchanging between the users. So game theory, in fact, predicts that in this trust game, both players will follow their economic-based best interest, and the sender will send 0, and receiver will send back also 0. However, in the experimental game theory, we usually do not see this kind of behavior. Here, what we see there is that there is a trust built between the sender and the receiver. So the sender will send a sum of money to the receiver, and the receiver is sending back accordingly. So it's in fact a sort of trust that is built between the two users. So we designed a trust metric in this repeated trust game that computes partner trust as a basis for the prediction of partner behavior. We defined the trust metric for a single interaction, so at the beginning for a single interaction, and then for an accumulating number of interactions. So for a single interaction, we have a current trust that is a function of send proportion. Okay, and send proportion is in fact the trustworthiness of a user in a single interaction, and it depends on how much the user sends to the partner. So we have the sending amount over the maximum sending amount. We also computed the aggregated trust score, which is a cumulative trust score over multiple rounds. We also took care that our trust metric deals with fluctuating user behavior, where we have a user that first tries to behave well and then would suddenly deviate. We designed an experiment with 30 participants where we tested variations of the trust game. We had a simple game where participants are given no information about partners, identity game where participants are given information about the partner identity, score game where participants are given trust score of partners, and the trust score here was computed according to our trust metric. And then we have combined game where participants are given both trust and identifier of their partners. So what we observed is that showing either trust score or identity of the user improves the measure, but showing both of them, so trust score and identity, does not change the measure relative to one of them. What we can say is that trust score or identity availability could significantly improve the level of cooperation between users, and by looking at a large-scale collaboration, so the trust-based systems could be a replacement of identity-based systems, especially in this large-scale collaboration where we cannot remember the identity of all the other users. So as a summary, I can say that my contributions towards an optimistic trust-based security for large-scale peer-to-peer collaboration. So what I did modeling of contract-based collaboration, computation of user trust based on user past behavior and prediction of their future behavior. And we also did the evaluation of this trust-based security using game theory and user studies. So now I'll pass to discussing some future directions of my project that is called Secure and Trustworthy Distributed Collaborative Systems. And I structure this project into three main axes: security for distributed collaboration without a central authority, user trust evaluation based on past contribution, and replication mechanisms for complex data. And I'll describe each one of them. So the first one on security for distributed collaboration without a central authority. I want to propose a security mechanism adopted for distributed collaborative systems without a central authority. And this security mechanism has to deal with the user access rights to the shared document, as well as to the end-to-end encryption, where we have to have a group key management suitable for large and dynamic groups. In order to avoid the use of a central server that stores all the data, I propose that access rights as well as data are replicated, and I propose to develop CRDT algorithms for the synchronization of access rights that will be composed with CRDT algorithms for data synchronization. And this work has to be easy to use and will be tested with users. And this work it will be done in the context of the PhD thesis of Pierre-Antoine Rowe, who started his PhD end of 2020. Regarding the second axis on trust evaluation, user trust evaluation based on past contributions, In my previous work, I focused on predicting the quality of the content of the document collaboratively written in Wikipedia. And in future work, I would like to focus on predicting the quality of a user contribution based on the quality of his past contribution. So for this, I propose to use the trust metric that we used for the trust game that predicts participants' future behavior based on their past behavior. This trust metric can be applied by considering that user contributions throughout the article are similar to user interactions in the trust game. What we need here is a novel of some what we need here is some new quality metrics for being able to evaluate the quality of a user contribution. So, for instance, we are looking at not only at how much is a contribution of a user, but also for how long an edit of a user persists on the Wikipedia article. This trust metric that we proposed, as well as the validation methodology, received a lot of interest from the Fair and Smart company for their personal data management platform that respects GDPR, General Data Protection Regulation, for computing the trust between the different users of this platform. We would be able to compute trust scores between users and enterprises based on their past interactions. So, for instance, it would be possible to compute a trust score based on the respect or violation of consents that were established before the collaboration. And now I pass to the last axis of research on replication mechanisms for complex data. So, operation-based and state-based synchronization have both advantages and disadvantages. Operation-based synchronization is more efficient since you only ship small updates, but requires an exactly once causally ordered broadcast. On the other side, we have state-based synchronization that requires only reliable broadcast, but features communication overhead by shipping the whole state. So rather than applying a single solution of state-based or operation-based algorithms, I propose to be able to combine them depending on the size of the updates and the size of the data state, and then we should decide at that moment which one to be applied. I also want to study composition of state-based CRDTs with operation-based CRDTs and with operational transformation. I'm also interested in the design of CRDTs for complex data, such as a relational database. Together with Wei Hai Yu from Norway, we already started to work on this topic. And in this complex data, we also need to maintain global invariants, such as integrity constraints. So I presented my work on large-scale, trustworthy, distributed collaborative systems. Due to the large-scale adoption of these collaborative systems, there are new uses and new practices that arise. And new challenges are emerging, such as consistency of complex replicated data in this large collaboration. Also, group awareness in large groups. Also, how to do user studies in these large groups. While we know to do user studies with several users, how we would do when we have many users, where we will need to also to have some simulated users in order to simulate the large-scale constraint. And we have to propose trust and security mechanisms without a central authority. So at the end, I would like to thank all my co-authors that are listed here. And thank you. And if you have any questions.